All right, so here we are in Chapter 9, Section 2. We're not doing 9.1, so this is 9.2, the first section. We're going to evaluate exponential functions, which just means we're going to plug something in to an equation that happens to be exponential, and then we're going to identify and graph using tables an exponential function. So first things first, we're going to define an exponential function. So an exponential function is the type of function in which the independent variable which you can see is also known as x, appears in an exponent, which we can also call a power, or that little number up there. So power. All right. An exponential function has the form of a function, so f of x, and then it's going to equal an a value times a b value that is being raised to the power of x, where a can't be 0 because otherwise this entire thing would be 0, and b can't be 1 because otherwise it wouldn't grow, and b can't be greater than, is greater than 0, because if it was negative, it ends up doing this like flopping thing, and that's not exponential. So either way, all the ones that we're giving you are going to have all of this, but just for reference. So taking a look at this graph here, you can see that we have our exponential growth. All right. So the first value here is our time in days, and apparently we start at 2 for our population of insects, it looks like, and ladybugs. In day 1, then there are 6 of them. Day 2, then there's 18, and day 3, there's 54. You can see that the population is growing by multiplying. So notice that instead of adding from one to the next or subtracting from one to the next, we end up having this value here, which is multiplying. And that's actually what we call our constant ratio, which we'll go over in a little bit. So again, you can see how what's happening is it's growing, but it's growing at this very fast rate, especially towards the end there. And of course, it's tripling. That's what this times 3 is. All right, so evaluating an exponential function. Again, remember, evaluate just means that we are plugging something in. So the function f of x equals 500 times 1.035 to the x models the amount of money in a certificate of deposit after x years. How much money will there be in 6 years? So notice that it says x years, and then they want us to plug in 6 years. So we now know that x equals 6, and we're going to plug it into the function that they give us of f of x equals 500, 1.035 to the x. So again, that little x there is going to become 6. So we're technically taking the function at 6. And so we'll take 500 times 1.035, raise that to the 6th power. All right, you can put this all in your calculator at once, but remember that the order of operations of PEMDAS say that you should do exponents first before you do multiplication. So there are some of you who will try to do 500 times 1.035 and then raise that to the 6th, and that is not going to be okay. So instead, it is in fact just this piece raised to the 6th, the 1.035 to the 6th. And so 1.035 to the 6th leaves us with 1.2293. That's going to then be multiplied by 500. And so if we multiply it by 500, we will get the amount of money in the certificate after 6 years. So after 6 years, we're going to get $614.63. All right. So again, main idea of evaluating our function, is that you do not multiply first. You bring it to the power and then multiply by that number up front. All right. So lots of blanks in this one, but here we go. So we need to remember that linear functions have a constant first difference. All right, so what happens is if I took 18 minus 6 and 54 minus 18 and 162 minus 54, I would get that first difference meaning subtraction. Then after doing our linear functions and constant first differences, we talked about quadratic functions. And so quadratic functions have constant second differences. And so remember that once we subtract each of these, we would then subtract what we had gotten as our results, those differences. And so then we move on to exponential functions. And exponential functions do not have a constant difference or any of those differences, first, second, third, or anything, but they do have a constant ratio, which I kind of alluded to in the last slides. Oh, sorry, I was going to write difference. All right, so taking a look again at what we were looking at in the previous example here are our constant ratios. And over here is just double checking that the x's have a pattern. So in this case, they're adding 1 each time, which is excellent because then our constant ratio makes sense. If one of these went 1, 2, 4, 5 or something like that, but then and still had times 3, then it would not be exponential at all. So we do want to double check that this is a pattern first before we even check that there's a constant ratio or not. So this means as your constant ratio, that as the x values increase by that constant amount, the y values are multiplied. So again, multiplied and not added or subtracted like the constant differences. This amount is the constant ratio. And is the value of b in our equation of a times b to the x. So this one here is that constant ratio. All right, so again, the b value, so notice here is 3. It's the thing that's being raised to the power. And notice that 3 happens to be the constant ratio as well. So those are supposed to match. All right, so the first thing we're going to do is identify an exponential function. And so all we're going to do is look at our y values or our dependent variables and see if they have this constant ratio. Of course, we're also going to check the x values to double check that those are going up at a constant rate before we even check the other ones. So if we take a look at part A, and the book often does this where they will show you how to do it with a table, but then they'll give it to you in a list. So a lot of times it's easier if you just rewrite what they give you in a list, in a table. And so in part A, we have our x values of -1, 0, 1, and 2. And so as you write them, you can see that those are in fact adding 1 each time to get from one piece to the next. And then the y values are going from -64 to 0 to 64 to 128. So taking a look at finding our constant ratio, hopefully you can already see that to get from -64 to 0, you would need to multiply by 0. And we can't have a constant ratio of 0, and so you end up noticing that it should actually be adding 64. And remember that adding 64 is not going to be a constant ratio or multiplying. And so in that case, this is our first difference. And so this is linear. And so in that case, A is linear and not exponential. All right. Moving on to part B. Our x values are 0, 1, 2, and 3. Our y values go from 4 to 12 to 36 to 108. And so if we look at our x values, remember we're trying to see if there is a pattern, and to get from 0 to 1 you add 1, 1 to 2 you add 1, and 2 to 3 you add 1 as well. And so there is a constant ratio or a constant difference here. So that's what we were looking for, just like in this one. And so then we move on to the y values. And so from 4 to 12, again, I'm trying to get a multiplier. So I multiply by 3. Then we double check. 12 times 36, is that multiplying by 3? And yes, it is. And then 36 times 108, is that also multiplying by 3? And you can always double check with a calculator, but it is. 36 times 3 is 108. So in that case, we do in fact have a constant ratio. And so because of that, we know that this is going to be exponential. And we know that our constant ratio is 3. So this one is exponential. And we'll just abbreviate constant ratio is 3. All right, so again, identifying an exponential function from a table just means, are the x's going up by the same number each time? Sweet. Are the y's being multiplied? All right. So to graph an exponential function, which we will be doing by hand, we need to choose several values of x. Generally, when we do that, we'll be doing -3 to 3. That's usually where the action is happening, over here around 0. And generate ordered pairs. We're going to plot the points and connect them with a smooth curve. All right, and it is going to tend to look like this graph here. When they are talking about, for instance, COVID right now, the idea here is that what happens is, if you are not doing anything to prevent, the growth of people being infected is going to grow exponentially. That's usually what happens here. So the idea is that, one person would affect maybe 2 people, and 2 people would then affect 4 people, and 4 would go to 8, and it would end up jumping. And so they do talk about flattening the curve. And so the idea is that they're trying to make it so that it would go more like this instead of your exponential growth. So again, this is your flattening of the curve that you're hearing so much about. All right, so kind of making it look more linear than this giant exponential growth. All right, so we're going to go ahead and graph this ab to the x. And remember that there were some requirements, but in this case, our a value, notice here, is greater than 0, so we have a positive, and our b value is greater than 1. And so we will end up referencing this later as we fill in a chart. So the first thing we're going to do is just go ahead and get each of these values. So in order to get our first y value, if we plug in a -3, 0.5 times 2 to the 3, -3, you would take 2 and raise it to the -3. So you'd end up having 0.5 times 0.125. And once you multiplied that by 0.5, you would get 0.0625. Now, that is a very small number to be able to plot here. So basically, you just graph -3 and practically 0. So notice I'm just kind of putting it right on top of the graph. Then we're going to do a -2. So again, all you're doing is taking 2 to this x value. So 2 to the -2 in this case. And then that number is going to be multiplied by 0.5. And so we'll have 0.125. If we plug in a 1, -1, that's 2 to the -1, and that's going to be multiplied by 0.5. So 0.25. Then we're taking 2 and raising it to the 0 power. Remember, that's going to be a 1, and 1 times 0.5 is 0.5. Then we have the number 1, so 2 to the power of +1 multiplied by 0.5 is going to give us a value of 1. 2 to the 2 power times 0.5 leaves you with 2. and 3 to the, 2 to the 3 power. That's a negative 3 times 0.5, you see with 4. So generally what happens with especially these decimals here is we don't necessarily plot each of them accurately, especially. So again, -2, a little bit more than 0. Then we finally get to something that's maybe a little bit easier to graph, -1 and then 1/4 of the way up. Then we have 0 and 1/2 of the way up. And then finally whole numbers, so 1, 1. Then we have 2, 2, and 3, 4. So you can kind of see that it's not linear here. It is very small and then growing pretty rapidly. And again, that's your exponential idea. All right, so that is graphing of 0.5, 2 to the x. So let's say that you do not want to take the time to do each of these steps every time, 2 to this power and then multiplying by that number out front. You can use your calculator to make this a little bit easier and more applicable. So if you go to the y equals and clear anything out that happens to be there, which it won't if you're using the online calculator, we can plug in what we have here and have the table generate instead of doing all 7 of these individually. And we did this with quadratic equations, so this shouldn't be entirely new. So first thing I'm going to type in is -1/4. Anytime you do a fraction, it has to be in parentheses. So -1/4. All of that is going to be then multiplied by 2, which we will raise to the x power. So going ahead and doing -1/4, then it will ultimately be multiplied by 2 to the x. So if we go to our table and scroll to -3, you now have all of, in fact, in one screen, the values that you're going to need for your table. So we have -0.0313, -0.0625, again, very much 0 at that point, -0.125, -0.25, -0.5, -1, and -2. And so as you go through these, again, these are very small. It's very hard to actually get these to be values on the graph. And so I'm just going to put them basically as close to 0 as possible, but not on 0. And so -2 is still there, and -1 is still there. But then we kind of get to the 4th there, and then -1/2 here. And then finally whole numbers. So 2, -1 goes down here, and then 3, -2. And so you can see that we're going to be following this trend here. And then if you continue on just to kind of see how it goes, so now you don't have to plug these in, you can see that at 4, we'd be at -4. Oh, I graphed that differently. That should be a 2. 4, -4, 5, -8. And then we jump off the graph. So this is actually the pattern because I wrote it down wrong. Let's see, or plotted it wrong. 3, -2. Yeah, I just plotted it wrong. All right. So ignore that part. Okay. So the only other thing that's happening here, and hopefully you can see that happening, is that every time that we graph this, even this one over here, notice that it's approaching this line here, but it's actually never going to cross it. Even if you go as far as you can in the negative direction, for instance, notice that it never actually gets to 0. These are all very close to 0, but not actually 0. And so we end up having this thing right here, dash. A lot of times they're indicated with a dashed line. But the idea is that you're never going to cross this. And when you're never crossing that, that's actually called an asymptote. So again, as you're graphing, just notice or note that you will never actually get there. And so a lot of times people just draw the line and kind of put it on the x-axis as they're doing it, but it never actually gets to there. So just as a precaution. All right, the next one here, we're going to graph this exponential function. Notice that each time we're doing it, we're changing just one thing to double check that we know what happened. So for instance, 0.52 to the x. and then we changed it to, instead of a positive number out front, we now have a negative number out front. This next one here is a positive number out front, but now a fraction instead of a number greater than 1. So we will be looking at how that affects what's happening. So going back to the y equals, clearing out what you have there, we can insert 4 times 0.6, and that raised to the x power. And then we can go to the table. You can have the graph it, but that's not really going to help you when you're plotting, because it does actually, it doesn't tell you those specific points. And so as you look at the graph, you can't just guess where those points are. So it's easier to go to the table, second table, and then get the actual values here. So in number, I'll do blue here. In plugging in -3, we're going to get 18.519. Plugging in a -2, you get 11.111. Oops, too many ones. Anyway, -1 is 6.667. 6667. 4 is 4. 0 is 4. 1 is 2.4. 2 is 1.44. And 3 is starting to get closer to that 0. So 0.864. So going ahead to plot this, we can't necessarily plot -3, 18, or even -2, 11, but we can kind of fudge it if we want. But we can graph -1, 6, and notice it's 6.6, so it's a little bit more than half. As long as you're between 6 and 7, it should be fine to look at. 0.4 is one of our exact values. 1 and 2.4, so a little bit less than half. And then over 2 up 1 and a little bit less than half. And then 3 and almost to 1, but not quite. So as we graph this, you'll notice that we're having this decline. And then it's approaching, of course, because it's an asymptote, it's approaching that axis. But of course, because of that idea that it's never going to cross that, as you graph it, just remember that there is this kind of dashed border here, because you have your asymptote as well. All right. So now that we've kind of looked at some patterns, so hopefully you notice the difference, at least between this one and this one here, right? Okay, so one of them is above the graph, one of them's below, one of them's decreasing, and the other one's kind of, well, it's decreasing as well, but decreasing very large versus decreasing to 0. So we're going to kind of identify some of the patterns. So if you ever have a graph that starts at 0 and goes up, that is because you have an a value that is greater than 0. And so notice that we are looking at our a value right here. Okay. If you have one that is going down, as we graphed in our second example, that's because the a value out front is less than 0. So that means it's a negative. Over here, that meant it was a positive. If you have it starting at 0 and going up or down, that is because your b is greater than 0. B is greater than 1. So taking a look back at the examples that we had, this example here looks like this one here, and that's because the a value out here is positive and the b value here is greater than 1. So that's why it looked like that. The next example that we did, started at 0 but went down. And again, that's because the a value was negative and the b value was still greater than 1. So again, that's why it followed this trend or this one here. Okay. Then the next one that we did, notice we have a very large value and then it goes down to 0. And so if we take a look at what the a value was in this one right here, the a value is 4, and so therefore it's greater than 0 or positive. Versus if the a value was less than 0, that would be negative and it would be down here. And then our b value, taking a look at what was in parentheses, is a fraction, or in this case, a number between 0 and 1. And again, I use the term fraction loosely because a fraction could, for instance, be 3/2, which is not in between here because it's 1.5. But the idea is a fraction or a decimal between 0 and 1 would have made it start kind of at these larger, what feels like larger values going towards 0. All right. So then we're going to do one last calculator application. Again, the first calculator application was knowing to go to y equals, typing in your equation, and then going to second graph or table up here in order to fill in that table. This piece here is going to use that table in an application. So in 2000, each person in India consumed an average of 13 kilograms of sugar. Yay for them. Sugar consumption in India is projected to increase by 3.6% per year. At this growth rate, the function, so they're giving us our function here, gives the average yearly amount of sugar in kilograms. And I just want to double check that you can kind of point out what's happening here. This 13 came from 13 kilograms, and this 0.036, because it's a percent, it's decimal. If you move the decimal place twice, is 0.036. So anyway, that's where those numbers are coming from. We'll do more of that in the next sections. Give the average yearly amount of sugar in, it gives the average, this function gives the average yearly amount of sugar in kilograms consumed per person after the year 2000. So again, if we're plugging in anything for the x, that means that it's the year past 2000. So using this model, in about what year will sugar consumption average about 18 kilograms per person? So once we get this value right here, which is the year, we would add 2000 to it, because if it became a 6, that means 2006. Or if it becomes a 5, that doesn't mean year 5, it means 5 years after this model was started. You'll also hear that as well as we're talking about COVID or listening to things that people are saying. They'll say things like, well, the models show. And so this is one of those ideas of a model. It shows where we started, what our growth is expected to be, and kind of how much time it will be until we get to certain amounts of infection or whatever it is. So again, this is a basic model, but that's the idea. So using this model in about what year? So we need to put 18 in for our our y value. So if we write the equation, f of x equals 13 1.036 to the x, what they want you to do is technically plug in an 18 right here and then solve. The problem is that once we start dividing by something, we won't actually have the algebra to solve. So we don't know the algebra here. So we don't know the algebraic steps to solve. And so instead, we're going to use the graph or the table. All right, so we are going to go ahead and try to find out when our y value, so remember that this is your y value, is going to equal the same as the sum of this value. So plugging in our equation, we've got 13 times 1.036 to the x. So 13 times 1.036 to the x. And then if we go to our table, again, we're trying to find a y value of 18. So notice we only get to 14 in this value here. So just continue to scroll down. You can scroll down in the y's as well. So anyway, we're trying to get to 18. And as you see in year 9, we're at 17, but in year 10, we're at 18. So taking a look at this, we're actually looking for in what year. And so it's not going to be in year 10, for instance, because in year 10 it already is at 18. So it's during year 9. And so you can see that these are some images of what they have done and the instructions here. But the average consumption will reach 18 kilograms in year 9. But remember that we were doing 9 plus 2000. And so that meant that it was in year 2009. And of course, this was previous projections. It's not really a projection. It's more like history. But anyway, so in year 2009, using that model from year 2000, that's what they would have projected. So, all right, so that's kind of a lot going on. A lot of times when we do models, we do not use the actual year value. We use the year value from when the model was initiated. And so in this case, 2009, again, was represented by 9 because it was initiated in 2000. So basically, anytime that you're given a graph that you're going to use to predict something, they will say that the X is in years and it starts at year 1980 or whatever it happens to be. So that is one thing to kind of look for. All right, so that was our 9-2 notes. And so hopefully you are now able to apply all of that to the assignment. You're going to be doing tables just as we had. You're going to be graphing, and then you'll also do one of the applications like we just did.